Alright, Assalamu alaikum. So in this video, we'll be starting off with one of the most hated chapters in O-level and math syllabus, and that is relative velocity. Well, personally speaking, this was my single most favorite chapter, and in this series of lectures, I'll try my level best to make you like this chapter as well. It's not as difficult as people often think it is. In fact, it's pretty interesting because this is one chapter, apart from permutations and combinations, where you really have to use your mind and visualization skills. You put all of them together with the mathematics and you try to solve the problems. So, as we always do, let's dissect the name of this chapter. The name is pretty self explanatory here. It says relative velocity, that is, the relationship of the velocities of different moving objects is going to be considered. So, relative means the relationship, and velocity is obviously displacement upon time. So, you can have a lot of objects in a particular relative velocity problem, but in our syllabus, we'll restrict ourselves to just two moving objects. So, relative velocity, in terms of what our syllabus requirement is the relationship between the velocities of two objects. Now, this is something which we encounter a lot. Many a times we have to make decisions based on relative velocity. That means that this chapter is not something that's confined to just the book and the questions. It has a lot of daily life significance as well, and there is a lot of significance in this chapter which is there in real life, even though me and you won't be encountering that a lot of times, but we can encounter those situations as well. Uh, the point that I'm trying to make here is that there are a lot of daily life examples of relative velocity. One very common example, which all of us experience, is while crossing a road. Let's draw a road here. Here's this uh, weird car coming here, and here am I. I want to cross this road. So, in order to cross this road, I need to make certain decisions in my mind. Should I cross this road? Should I not cross this road at this particular point? And if I can see that this car is coming at an extremely fast pace and my pace wouldn't be sufficient to be able to cross the road, I'll decide to not cross. Likewise, if this car is coming at a moderate pace, I can make up my mind that alright, this is the speed that I should take to cross the road safely. So, what are we doing here? We are comparing the velocities of the car and our potential velocity in order to cross the road and avoid impact with the car. So this is one example of relative velocity in our daily lives. Another example is on the roads. Again, let's say that uh, this is your car here traveling at 60 kilometers per hour. And here's my car which is traveling at 80 kilometers per hour. Yeah, I am a fast driver. Right. So what will happen is that over time, the distance between the two cars, yours and mine, is going to decrease. Why? Because I'm 20 kilometers per hour faster than your vehicle. And over time, what will happen is that I will be able to overtake you. Another example of relative velocity is when, again, see, in this case, both objects were moving. In this case, again, both objects are moving. And the third case that I'm going to discuss, in that also both objects will be moving, but relative to one another, they'll be stationary. You might have seen on the on the roads that what happens is that two motorcyclists are traveling side by side and conversing very happily with each other without encountering any problems. Why is that so? Uh, Even though both motorcyclists are moving, but they are doing so at exactly the same speed. This means that for this particular motorcyclist is stationary, and for this particular motorcyclist is also stationary. Therefore, no gap develops between the two. Another way to understand this would be through this example. Let's say my car is also traveling at 60 kilometers per hour. Then what's going to happen is that the distance between the two cars is going to remain uniform till the end. The same thing happens here. Even though both motorcyclists are moving, but the movement is at exactly the same speed, therefore, both of them appear stationary to each other. Both appear stationary to each other, and therefore conversation is not a problem. So through these three examples, we have established that relative velocity has daily life applications as well, and there are also other real life applications which we don't encounter on a daily basis. But when we'll solve questions, we will see that relative velocity does have very important real life applications. Having established the importance of the study of relative velocity, let's now come to the conceptual parts of this chapter. And the first conceptual part of this chapter comes with the name of the chapter itself, and that is velocity. From what we have studied in O-level physics, we know that velocity is a vector quantity. That means it has a magnitude and it has a direction. Then there's another part here, relative. So when I have to study the relationship between the velocities of two objects, I might have to carry out addition, I might have to carry out subtraction. We won't be doing multiplication and division. So I'll have to carry out addition and I'll have to carry out subtraction. But in order to carry out addition and subtraction in vector quantities, you have to keep into consideration both the magnitude as well as the direction. So if I have, let's say, an object moving at a speed of 10 meter per second and a bearing of 60 degrees, and I have another object which is moving at 15 meter per second and at a bearing of 120 degrees, I cannot find the sum of these two velocities by simply adding the magnitudes and saying that my answer is 25. This is incorrect. Why? Because I need to keep into consideration these directions as well. So this means that I need to use some other method. And we have studied this other method as well in O-level physics, in O-level math, and O-level add math vectors as well. We know that there are primarily two ways in which vectors can be added together. And that is the parallelogram method or the triangle method. Triangle method, which is also known as the tip to tail method. In this chapter, we will prefer to use the triangle method of vector addition in order to add or subtract velocities. So let's take this very example only. What I'll be doing is, I will be adding uh, this velocity and this velocity together using the triangle method, also known as the tip to tail method. Let's quickly review what the tip to tail method was. I'm writing this down here. If you don't know, you should copy this down with yourselves. So what we do is that we first draw the two vectors, then what we'll do is that to the tip of the first vector, attach the tail of the second vector. The resultant vector will be obtained after this. After this, that is, after attaching the tail of the second vector to the tip of the first, the resultant vector will be obtained by attaching the tail of the first vector by the tip of the second. So let's do this. Now, whenever bearings are involved, the first step would always be to draw a small compass with us, because bearings are always taken relative to the north direction. So drawing a compass is always very useful in order to decide the direction. So because it's a bearing of 60 degrees for the first vector, this is somewhere this vector would lie. Here we have 60 degrees, and here we have our vector with magnitude of 10 meter per second. The second vector has a bearing of 120 degrees, so that would be 90 and 30. This would be my second vector, which has a magnitude of 15 meter per second. So in the first step, what we'll have to do is, now if you take a look at this orientation, this is not a tip to tail orientation. Why? Because this is the tip of the first vector and this is the tail. Here what we have done is, we have attached both the tails together. So this is not tip to tail. In order to make this tip to tail, what I'll have to do is, I'll have to transfer this 15 meter per second vector over here, so that the tip to tail orientation is achieved. So this is exactly what I'm going to do now. So here comes my vector, 15 meter per second. And what about the resultant? The resultant vector would finally be obtained by attaching the tail of the first vector to the tip of the second vector. So this would be my resultant vector. Let's say this is R. So I need to find what R is. Right. Having drawn this triangle, I will now use the angle properties that we have studied since class 7 to find out some of the angles here, maybe this angle, whatever. And then we'll use trigonometry in order to evaluate the resultant vector. So let's do this. Now this entire angle was 120 degrees. And if we subtract 60 degrees from here, the remaining angle here would be 60 degrees. And we know that this 15 degree vector and this 15 degree vector, both of these are parallel lines. And this 10 degree vector is kind of a transversal between these two parallel lines. Therefore, this angle here and this angle here are actually interior angles. So this angle would be 120 degrees. I'll just write this here. So this is 120 degrees. Right. I can now use the cosine rule to find r. The magnitude of r, just by the way. So the magnitude of r can be given by 10 squared add 15 squared minus 2 times 10 into 15 cos of 120 degrees. And all of this has come under the square root sign. So I'll just do my working here on my calculator. Angle input should be degrees. So this is 10 squared, add 15 squared, take away 2 into 10 into 15 times cos of 120 degrees. And the answer is coming out to be 5 root 19 meter per second. But remember, the work is not done yet. We also need to find the direction of this vector. Why? Because a vector also has a direction, not just the magnitude. So I'll have to find the direction as well. So if somehow I can find this angle, because this is the triangle that we have, and add 60 to this, I'll be able to get the bearing of the resultant r. So how can I find this vector out, or this angle out? Let's call this angle theta. We can now use a sine rule to evaluate theta. How? 5 root 19, which is the magnitude of r, upon sine 120 gives us 15 upon sine theta. Let's do our working. 5 root 19 sine theta is equal to 15 sine 120. Theta would be sine inverse of 15 sine 120 degrees upon 5 root 19. I'll enter all this information in my calculator in one single step. 15 sine 120 upon 5 root 19. So this angle theta comes out to be 36.5868 degrees. I'll add 60 to it and I'll get the bearing of r. So how will I write my answer? The answer would be add 60. That r has a magnitude of 5 root 19 at a bearing of 096.6 degrees, correct to 1 decimal place. So we have reviewed how to add vectors. Now let's talk about subtracting vectors. What I'll do is I'll give these vectors names. I'll call this vector as A and I'll call this vector as B. So what I want to do now is I want to find A, take away B. Now the easy way to think of A take away B is that it's actually A add negative B. And what is negative B? Negative B is actually exactly the same thing as B but in the opposite direction. So let's come to the diagram that we have drawn above. If this is vector B, then negative B would be the same thing but in the opposite direction, so it would be here. This is negative B. It has the same magnitude of 15 degrees, but the direction obviously is reversed. After this, we will follow the same rules of vector addition to find the difference. Let's do this. Let's draw the diagram again. And the first step, draw the compass, because we have bearings. Whenever we'll be having bearings, we'll be drawing compasses. The first vector is a 60-degree bearing vector at a magnitude of 10 degrees here. At a magnitude of 10, sorry. The second vector, which was actually positive B initially, was a 120-degree vector here. Right, so this is how it will be made. However, we are concerned with negative B here. So negative B would be this way. And what will be this angle? we can see that both these lie on a single straight line. Says this is 120 degrees, this would be the supplementary angle to this angle, and that is 60 degrees again. So again we have a magnitude of 15, this vector is negative b, this is a, and I can now remove this vector from here. Now since I want to use the tip to tail rule again, and this is not a tip to tail orientation, so what I'll do is I'll transfer this negative b vector to the tip of vector a. Here we go. So this is negative b now. And the resultant vector would be obtained again by attaching the tail of the first vector to the tip of the second vector, something like this. It's not very exact, and you won't be drawing exact diagrams as well. These are scale drawings. The working has to be done using trigonometry. Right. So this would be A take away B vector, which is our resultant vector with this direction. Right. So the first thing that we need to do is we need to find this angle out somehow. And that's again very easy stuff. How? Because this vector negative b and this vector negative b are obviously parallel to each other. So this angle right here and this angle would be supplementary angles because they're interior angles. This whole angle is 120 degrees. So this angle would be 60 degrees. Again, we can use the cosine rule to find the magnitude of A take away B. A take away B is calculated by 10 squared, add 15 squared, take away 2 times 10, 15, cos of 60 degrees. So we have cos of 60. The answer comes out to be 5 root 7. This is the magnitude. We still need to find the direction. So somehow I need to find this angle out and then subtract 60 to get this angle, and then subtract this angle from 360 to get the bearing. Let's start. We'll first find this angle out. Let's call this angle theta. I can use the sine rule again. So it would be 5 root 7 upon sine 60 is equal to 15 times 15 upon sine theta. That means that theta would be 15 sine 60 degrees upon 5 root 7, and all of this would be sine inverse. So I'll enter this information in my calculator. Sine 60, 5 root 7. So theta comes out to be 79.1066 degrees. Now if I subtract 60 from this, I'll get this angle, which is 19.1066 degrees. Now since all directions were given as bearings, so I'll have to state the direction of the resultant also as a bearing, which would be this. And this is a complete 360 degree rotation minus this small 19.1066 degree segment. So I'll simply subtract my answer from 360 to get my bearing, which is coming out to be 340.9 degrees. So let's quickly review how we carried out subtraction. Subtraction is done by again using the tip to tail method, but this time the vector that comes after the negative sign, it would be reversed in direction because of this property. So the key taking points from what we have covered up till now is that relative velocity, firstly, is the relationship between the velocities of two moving objects. Then I told you that this chapter has a lot of daily life examples as well. And then I told you that velocity is a vector quantity, which means it has a magnitude as well as it has a direction. Therefore, adding or subtracting the velocities would require a diagrammatic method so that we can keep both the magnitude and direction into consideration. The diagrammatic method that we will be using is the tip to tail method. And in the tip to tail method, what we do is we first make one vector, then we attach the other vector in a way that the tail of the second vector is attached to the tip of the first vector. And the resultant is obtained by attaching the tail of the first vector to the tip of the second vector. Then we'll use the angle properties that we have studied previously, and we'll use trigonometry to find the required angles and the required magnitudes. This is how addition was carried out. Subtraction was done by the same tip to tail method. The only difference was that if I have a vector A and a vector B, which are being subtracted from each other, then the vector that comes after the negative sign would just be reversed in direction, and we'll follow the tip to tail rule again. If you have any confusions in using the tip to tail method for vector addition, you can ask me personally. I'll inshallah ta'ala try to guide you guys out. So we have done quite a bit of foundation making for this chapter. Now remember, since this is a chapter on velocity, and velocity is actually displacement upon time, so you can be asked to find out velocities as well. You can be asked to find distances and times as well, because they have a direct connection with velocities. So you should be mentally prepared for this as well. Now finally, the last thing that I want to cover in this video is something called the relative velocity equation. Now before we come to the relative velocity equation, we need to understand this thing. See, when we are studying the relationship between the velocities of two objects, we definitely have to take one of those two objects as my reference point. Right. So let's take an example here. Let's say that I have one object here, this object A, which is traveling at a velocity VA. And I have another object here, which is traveling at a velocity VB. Right. Now, if I am taking B as my reference, if I want to make B my reference velocity, that is the velocity with respect to which I would now be studying the velocity of A, then this is my new axis. Alright, I'll first do it with A. I'm making A my reference velocity. So this is my new axis. Because this is my new reference point, the initial reference point is obviously the y-axis here. But now, because I am making A my new reference velocity, so this is my new axis. Now, in the initial condition, this was the distance VB, and this was VA. But now that this is our new axis, the distance between A and B would be considered, and that would be given by VB take away VA. So the velocity of B with reference to A would be given as this. So velocity of B with reference to or with respect to A is given as velocity of B take away velocity of A. This entire statement is abbreviated as velocity of b slash a. And this is what is the relative velocity. So we can say that the relative velocity of b with respect to a is given by velocity of b minus velocity of a. Now what I'll do is I'll change my reference point. I'll draw this diagram again. Here is a at VA and here is b at VB, and this is my new reference line. Now we can see that the distance between A and B again is the same, that is VB minus VA, but there's a difference. In this diagram, this velocity VB was ahead of the axis by VB minus VA units, but here the velocity that we are considering, that is A, is VB minus VA units behind the new axis. So because it is behind, we'll write a minus sign here. So this tells us that the velocity of A with respect to B is actually, if I do some solution here, this would give me VA minus VB is VA minus VB, and using both of these, we can say that velocity of B with respect to A is negative of the velocity of A with respect to B. That means reversing the reference points reverses the sign of the relative velocity. Again, this can be said to be the relative velocity of A with respect to B. So this brings us to a relative velocity equation. The relative velocity equation states that the relative velocity of an object A with respect to another object B, where B obviously is our reference point, right, would be given by velocity of A take away velocity of B. Now when I am saying that this is the relative velocity, this does not mean that I have changed the velocities in any way. The true velocity of the object at A still remains VA, and the true velocity of the object B still remains VB. VA slash B is just the relative velocity. That is, if I am taking both objects in context of each other and not their entireties, then VA slash B would be the relationship between these two velocities. This means that this velocity and this velocity will be called the true velocities of the objects A and B, whereas this would be the relative velocity. So the crux of this discussion was that while calculating the relative velocity, we are not taking any credit away from the true velocities of the objects. The subtraction is being done just to obtain a relationship between the two velocities with respect to a particular reference point, which comes after the oblique sign. So this is a relative velocity equation. In your questions, you might be given the relative velocity, or you might be given the two velocities, or you might be asked to find one of the two velocities. So the things to remember about the relative velocity equation are that number one, this is an equation of vectors. So you cannot use this equation arithmetically at all times. Taking the example of these two objects once again, if I want to find the relative velocity of A with respect to B, I cannot simply write 10 minus 15. That would be completely incorrect. So remember, this is an equation of vectors. And the main use of this equation would be to help you draw a vector triangle, which will then be resolved using trigonometry and angle properties to help us find whichever vector we want to find out. Remember, the relative velocity is also a vector, the true velocity of A is also a vector, and the true velocity of B is also a vector. So, the conclusion is that this equation is not an arithmetic equation. You will not plug in the magnitudes of the vectors directly and do your calculations. That's an incorrect approach. Instead, you will use this equation to draw a vector triangle. Then you will resolve that vector triangle using angle properties and trigonometry and find the resultant vectors and or the resultant directions. I hope all that I have explained in this video is extremely clear. In the next video, we'll be starting off with river crossing problems of relative velocity. Till then, Assalamu alaikum warahmatullahi wabarakatuh.